Is the voice on?
I think so. It showed it on before. It was showing the thing moving.
Okay.
So I tested it. Let's bring that close down there. Okay. So.
No longboard?
You got the bad weather board.
Oh,
Is it about to be bad weather?
it poured for like
It
a
is.
solid hour.
Okay. I did not bring my umbrella.
It stopped.
All right. So what do you? This is a time for you. What would you like to cover today? I can pick random problems out. Because the other ones we have, I've done the videos where I've covered some of the problems, but I figured, and we also have the solutions posted. So I thought maybe I would just pick a random problem, or you could ask, you have a request, I'll take it.
It's a, yeah. So, I think it's the first problem in the review. On the review, so you see, like, on this one, it asks us to find the combined stresses on element A, while usually, like in class, we've done the ones with element B, or for homework we've done element B.
Yep.
What are the main differences in terms of finding the combined stresses? What are the differences when trying to find them?
Well, for the a lot of times for this, like B would not have any bending to it, right? Would not have any bending stress because it's on the neutral axis.
Okay.
But A will not have any transverse shear. Because if you look at the force, I think it's labeled just F, yeah. That F, that causes transverse shear at B, but it doesn't cause transverse stress at A. So that's really the big difference in this scenario.
So it only matters towards the end of the problem when you're trying to actually.
No, really more towards the, this is probably an overly simple problem, I think.
Okay.
I started out with one that I would envision asking a student to solve. Hey, solve this problem, and then just to try to organize your brain. Because sometimes the door handle ones can be a little overwhelming for someone that's like just completely lost. So this is sort of like a one to try to help those people out. That's why I chose it. To put the thing in there. I think these actually came from my notes from college. Actually, this figure.
Oh wow.
I scanned it in at some point.
It's a good scan.
Yeah. Okay, so is there a particular kind of problem? We just talked about principal stresses. Maybe we want to run through a principal stress problem. Yeah, seems fair. Okay. Let's pick one out. So in order to make this useful to people. I don't know. Can we zoom that in? I don't know. I think it's going to come out okay. Maybe. We'll hope. We can hope. I don't want to see myself in this camera this time. All right.
You can adjust it.
Yeah. Can you adjust that for us? You can zoom it the old-fashioned way. Let's pick some out of the book, I guess. And we are in chapter 3, and there's actually a couple trick ones in here, I seem to recall. We're not going to pick the trick ones now. So maybe I'm going to pick problem. This is from the 11th edition. And pick problem 315 and go sigma x is equal to, so I guess this is, I'll pick C. Sigma x is equal to 10 KSI, they call it KPSI, I think it's silly. And we have 20, I go C at 24. And then tau xy is equal to 6 KSI, and they're saying it's counterclockwise. So if we don't have already the stress element labeled, we should label the stress element ourselves. And declare where X and Y is. That's a good idea. And both of these are positive, so they're tension, or they might be, someone might write tension next to them, but I think the book and the problems do is positive and negative. So this is going to be the 10 KSI. And this is the 24 KSI. And then this is the XY, so that's the X face and the Y direction, and it's counterclockwise. So that makes it go that way, right there, right? Did I get that right?
Counterclockwise. Yes.
So now we know all the others. And that's going to be 6 KSI. So, nice to have graph paper to do this, but we could get kind of close. I guess because this is the biggest one right here, we might want to use that as the reference. So I'll go maybe 5, 10, 15, 20, 25. I might have exceeded it too large by there. But, and I didn't do a great job of keeping those really incrementally bigger. 5, 10, 15, 20, 5, 10, 15, 20. All right. So my first thing is to always plot out the points when I'm making a Moore circle in this way. So I look at this face first, and I say I got 10. All right, so there's 10. And on this face, it's going counterclockwise, so that's the convention, is that we go clockwise on the top and counterclockwise on the bottom. So we're somewhere right in there somewhere. And then we do the same thing for the top. We see 24, so here was the 10. So my 24 is like somewhere right up there, and my 6 is kind of like right there. Okay, eyeball a line that goes through the. I guess that's okay. And there's about where my center is going to be. And we don't have to, but we could label this and go 24 and 6. And then this one down here. We might get in the way of our other circles because of this, but I'll write it really small. This is going to be 10 and negative 6. And I'll lay this as C.
So if on the stress element, the 10 KSI and 24 KSI, we're going in the opposite direction to be on the other side of the graph, correct?
Only if they were compression.
Okay.
Yeah. So the.
So if they're like
I thought if you, I wasn't sure if you meant you would flop. Which one was like that was 24 and that was 10.
No, like 10 was going this way.
Yeah. If it was compression. Yeah, if it was compression, it'd be over on this side.
Okay.
So what I always do first is I go to find the center of the thing, which is going to be the average. So it's 24 plus 10 divided by 2. Is that 17? I think so, right?
Yeah.
Because 34 divided by 2. Okay. And then find the radiuses where people get the most messed up on the way that I'm trying to teach it. In this case, it's easy. It's just as easy to use this length as it is to use this length. I'm arbitrarily picking this one to find my radius.
Quick question.
Yes, sir.
Why'd you why is the 24 with the positive 6 and the 10 with the negative?
I'm just saying. Well, this is the negative 6 is just the fact that it's counterclockwise, and the convention. A lot of books use. This book does too. Is that the counterclockwise is here on the bottom. There's little squares trying to grab my face on the thing. It's very distracting. Is that cool?
What's the trick to remember with which direction the torque points? Like whether it's a clockwise or counterclockwise.
This is good right here. Okay, so he's saying counterclockwise right here. Well, he's being specific about what face he's on. This is the face and this is direction. That's the traditional way. And so the one on the top, like this guy right here, is technically going to be tau yx, because that's his face, and then that's his direction. Now, some places they decide to give this a positive or negative sign, and that just means that like it's either on the positive face it's in the negative y direction, on the negative face it's in the positive direction, right? Which would be just as true from here. But this book decided to give it counterclockwise, and you could look up in the book, because you have that available during the exam, and see that the figure has like this little thing on the bottom and this little thing on the top. So, or maybe sometimes it says CCW on the top, bottom, and it says CW on the top. So they told us it was counterclockwise, so that must have been going the opposite way of a clock, right? That's clockwise, that's counterclockwise. Is that? Okay, cool. The radius, like I said, this is sort of like sometimes a trickier thing for people, so I try to communicate as best I can. We're just trying to figure out what these legs are, right? So we're taking the square root, and the horizontal leg is going to be my 24 minus my 17. Because I know that's 17, and I know that's 24, so I want the horizontal distance right there, squared. And then I also want the vertical distance, which is just going to be my shear stress. And we need to use a calculator for that probably. So we go 24 minus 17. I should be able to do that in my head. I think it's 7, but let's just be sure. There you go, 7 squared. And then we have 36, add it, take square root. So we get 9.2, let's go 22. It's 2195, so I'm just, okay, so now I go on to make my, I'll try to make my circle. It's nice to have a compass when doing this, but you can like sort of plot it out. First, you can look and say, well, you know that the top of this is going to be above the center. Boy, that's not looking very good right there. It's not looking very promising. Somehow, for my circle. I'm going to double check this. Did I do that wrong? 24 minus 17. Yeah, I guess so. It just doesn't. I'm looking egg shaped here. I guess I just didn't do a very good job. So let's try to make that as best as we can. But one of the reasons why I want to make a sketch of this thing is to try to do as a sanity check, right? But it also has like sort of a physical meaning to it. So I didn't do a very good job of my circle. I expect more out of you than me. That's not true.
When you found the result, that's just the general formula?
This is just the radius of the thing, and I'm literally just trying to do the graphical, just doing the graphical of the thing.
But to find the radius, that's just the general.
You can have there is a general formula for this. So just to be clear, I would like to have the more circle drawn because it has a good physical meaning on there. But if you wanted to, you can use the equation, right? So let me switch over to, I did this right here, boom. Right, so, see, the thing is, it's got its own shadow on it. You can see that you can see they have a radius right there, so that is on the page. This is available too. By the way, there you go. There's your counterclockwise thing at the bottom to try to remind you of where it is. So you find the center and you find the radius. But aside from that, there is also a general formula, and I think they should have made these A and B instead of 1 and 2, because it's confusing. Because many pages after this, they tell you, but 1 or 2 could be 0. because there's 1, 2, and 3. Right, so, and then later in the book, they use the non-zero ones, they call it capital A and capital B subscript. So I wish they would change that, because you go over to just a couple pages later, and they tell you, oh, by the way, there's 3 more circles, and so that's more of a generalized thing right there. So that is a very generalized thing, because it has that scenario where there are stresses on every side. But as I mentioned, as a practical matter, there's only one scenario where there's ever stresses on more than 2 sides, and that's the inside of a pipe might have it. So continuing on, anyway, let's see, we're gonna, brown's almost dead now, so it looks like chocolate milk. So we find, I like to call it A, is going to be R plus C. All right, so I can barely read that. Now I can see. So you're going to say it's going to be 17 plus, well, I should really say C plus R. I think that's usually what it is, C plus R. So I say that's going to be 17 plus 9.220, can almost do that in my head. That should be 26.90, 26.22, I mean. And these are all in KSI, so that's KSI right there. So that should be like right there. It's not too terribly bad in terms of my graph. My sigma B is C minus R. And that's going to be 17 minus 9.220, which I will have to do. And that's 7.78. And I could have got another sig fig probably in there, so I'm probably off by a little bit. And we can see that that's going to be here. Now we're in the space, you know, we're in the shape to go, oh, this is going to be sigma 1, this is going to be sigma 2, and sigma 3 is going to be 0. Just put that anywhere. And now I say, hey, I want 3 more circles. And you're like, well, I don't know what to do the other 3. Well, they're just having that guy right there, and then the big Moore circle. And the most important one for later on use is the abs max, is the top of the biggest circle. When I say I want a fully labeled Moore circle, this is pretty much what I want. I don't necessarily need the coordinates, but I do want sigma 1, sigma 2, sigma 3, and tau abs max. I'd like to see where you plotted the points and have this thing. C and R, those are nice to have as well. I would like to have those, but yeah. And then so when you answer, so the last one we want to get is the tau abs max. Is going to be sigma 1 minus sigma 3 divided by 2. So we could relabel all of these. That's sigma 1. This is sigma 2. And we know that sigma 3 is 0. So we have 26.22 minus 0 divided by 2. And I should be able to do the 13.11 in my head, right? So the very last thing, I want to summarize the thing. I'll switch to just 3 sig figs. And then tau abs max. 13.1. It's supposed to say max. there are two other cases usually, not too terribly different. 4 more circles. The most common is to have it crossing, one side's compression and one side's tension. Another would be to have it both are compression. The only complication to going through this method right here is making sure that you find what the radius is going to be onto there. It'd be nice if I had these answers in the back of the book, but I don't think I have. I think this one has the odd and the even answers. If it has any, I think it still does. No, these are in there. Oh, they also have the angles. I don't ask for the angles in the problems, but you can ask for the angle, and that's. I'm not going to ask it, so you probably don't care. But what you do is you find what that angle right there is going to be, and this is twice the angle of what the angle that you actually would rotate the stress element. Because everything on here is twice the angles of everything. So in order to get the absolute maximum shear, you actually rotate it 45 degrees, but on here it's 90 degrees that you rotate it.
So just to prove, this is a 3D Moore circle, not a 2D one.
This is the 3D Moore circle because it has 3 circles.
Gotcha. Okay.
Right. So we can see all 3 main views that we would have as part of it.
Okay.
Oops. Keep looking for that video. So let's see how we did with the numbers. We were C, right? So 26.2, 7.78, and okay. So I think they're just talking. Okay, so they didn't do the 3D Moore circle yet. I don't think this problem is asking for 3D Moore circle yet into the thing. For whatever reason, they decided to make a distinction between problem 315 and I think a later problem that's in there. Yeah. So 318, they start asking for the 3 principal stresses onto the piece.
And you would ask it like that, just give us.
I would give you instructions every second what to do. Okay. I might even label the stress element for you. I don't know.
Okay. But you wouldn't ask us in a sentence, or.
I don't know what I would do. Sometimes I combine this with a pressure vessel.
Okay.
But not the inside of a pressure vessel. Just because I like to ask 3 questions instead of 4 questions. It depends on what I'm doing.
Okay.
Yeah, I haven't written the exam yet, so I haven't decided what it's going to be. It's probably not going to be much different from some old ones.
Is sigma 3 always 0?
No. We could have a scenario here where redraw on top of this area over here, where so let's say that on our stress element we had tension and compression instead. So we would plot the thing out over here and maybe we'd get a point like right there. Maybe that would be, well, I guess it would be down here, right, because of the way I have it drawn. So let's say that that's that face. But over here, let's see, I kind of messed myself up by going so high, but it would be, I'll make it down this way. Here you go. But we don't know what the value is, but we know that value and this value are supposed to be the same. Let's pretend I got it right. So we'd have this main Moore circle right here. Something like that. Now this is sigma 1, and this is sigma 3, and this is sigma 2.
Okay.
It's because there's no stress coming into and out of the board. That would be the plane that would contain the zero. The
But
zero is
one
part.
will always be 0.
Yeah, one of them will always be zero, except in the case of the inside of a pressure vessel, because that now you actually have a cube that's actually taking place, right? So now you want to have. You would have, like, let's say, here would be the stress that we're looking at. Here's the one that we just drew onto there. And then, like that for the shear. But now we might have a compression that would be acting in this direction, in the radial direction. And that would generate a more circle. A lot of times that, by the way, because of the way that, that pressure is going to create stress on the in the tangential direction, the hoop, and the longitudinal. A lot of times that radial is going to be pretty small compared to the others. So if there was only tangential and longitudinal, one thing to note is that they are always twice, or pretty close to being twice each other, right? So that let's pretend there's no shear on there. So this guy right here, he's the tangential, and he's going to be the longitudinal right in there. Right, and they're both tension. But we might have one over here where that's the radial. Right, so now we don't have one that's zero. So here would be, this guy is sigma 1, this is sigma 2, and this is sigma 3. And they always go in that order. 1's the furthest over to the right, 3's the third one's the furthest one over to the left, and 2 is in the middle somewhere. So we could that is possible, but and worth knowing about, because most important aspect of this is this guy, because this is always true, right? The absolute maximum is always sigma 1 minus sigma 3, but sigma 3 might be negative, so that makes for a larger tau abs max. Because as we'll see in chapter 5, one of the failure theories is based on how large that number is. Okay, what kind of problems I see? Pressure vessel problem? Here's one I've actually asked before. I'm always looking for new and interesting problems. So here is one that I'll write it down on the board. I think it's problem 124 from, this is the same textbook you should have used for mechanics and materials. Beard Johnston. Let me see if we get the binding to straighten out right here. Maybe I'll trick it by putting a pen underneath it. So we can actually read the words. Yeah, something like that. Okay, so I'll erase this and do that and write up the thing right here. So this is Beard Johnston, and we might alter what the problem is based on, I don't recall what the stress element they want us to use is on here, whether it's K or L. Maybe they're asking for both of them. We don't have to do both, but maybe they are. So they're saying this thing has little dome looking thing on here, and it's got a collar. It looks like anybody a Doctor Who fan? Doesn't it look like a Darlac? No, I guess not.
Exterminate.
There you go, yeah. Everybody together.
Exterminate. Just run up some stairs.
Then they can fly.
Oh, that's right, they did. You
See,
know that.
my best friend growing up in New York, he was up the hill just enough. They were able to get PBS, and they had repeats of Doctor Who on there. And they didn't get it. I didn't get it at our house. So, I know it's a sad story, right? It's a tragedy, is what that is.
It's a damn shame.
It's a damn shame. So he would always want to play Doctor Who things, and I just had to take his word for it. And then when I actually watched them, I have to say I was kind of let down. He made them sound a lot more interesting than I think they, at least that was my perspective. I apologize if I'm offending anyone.
I mean, their laser was a whisk, so. And the sucking device was a.
I think he had to have a pretty good imagination too. I really enjoyed it. Okay, so there's a 150 millimeter radius, I guess. And other information here is that it's, which one are we looking at? 124, right?
Is this 124, but the thing says 124 as well.
So which one is it? This says 124, right?
Yeah.
A compressed air tank has a 250 millimeter outside diameter. Okay. Oh, I see this because the edge of the thing, that's why. So that little part of B is further out than the diameter. So I was, this, no, I had that right. That's the right dimension. But like to the outside of this thing is like 125. Yeah, okay. So it's just where the bracket goes. And so the outside diameter, they say outside diameter, is 250 millimeters. And the wall thickness is 8 millimeters. And it's got a collar and there's a 40 kilonewton. So P is equal to 40 kilonewtons. And knowing that the gauge pressure is, so you know, it's sticky that they use P in here. Because I want to use lowercase p, and you can't tell the difference between uppercase P and lowercase p on a board. But they got 5 megapascals is the pressure. I'm changing it to F. I'm making a decision here. That's F. Because P, why do people use letters other than F and R? I don't know. I guess I'm not in charge of the world, so I don't know. Determine the maximum normal stress and maximum shearing stress at K, and then also at L, right? So problem 125. Yeah. So this guy, which one's K and which one's L? This is K. This is 124, and this is 125. So I think 125 is going to be a little bit more interesting, but we could kind of do both, but it's just going to take up a little bit more of our time. So let's. I got a Darlock right there. I'm not even saying that the right way. Okay, so the big difference between these is really going to be the L is going to have compressive bending stress. K is on the neutral axis that would be created here for the bending. Can you picture that?
Because K would have transverse?
You
shear?
would have transverse shear at K,
Okay, but not at L.
But not at L. Yeah.
Okay. Oh, okay, that makes more sense. Yeah.
I like it. It's my favorite song. All right. So what I might do is I first would probably want to figure out what my outside radius is. I could do that in my head, 125. I think I got it right. And now, so maybe I want to have my T over R, and my thickness is 8 divided by 125, and I bet that's pretty small. All right, so that's 0.0640, so it's less than 0.1, therefore it's thin. We don't have to waste our time with the longer, thick wall equations. So we might want to go for the average. Okay, so we also might want to find, if we're going to use our equations correctly for Shigley, he likes to go the, I keep doing this one, he likes to use the inside radius. So the outside radius minus 2 times the thickness I said radius and I meant diameter. So 250 minus 2 times 8, and that's pathetic. I think it's 234, is that right? 234. 34 millimeters. This is only going to get worse. I'm getting tired. So we could find the tangential by taking P times di, dividing it by 2t. Be careful not to pick the one that has di plus t in it, because that's actually, in Shigley for the maximum, which is inside, on the inside surface. They don't have one that is meant to be for the outside surface. They only have one that's for the average. And just as a word of precaution, I will point out where I'm talking about as the reminder is right in there. You could see that we have the average is P times di divided by 2t, whereas the maximum, but that maximum occurs on the inside. So we're just going to use the average one. This one.
So one doesn't exist for just the outside?
Nope.
Really?
No. Well, honestly, if you were to go to this book right here, they don't even bother with making a distinction between the inside radius and the outside radius. They just say the radius, because it's thin. But I just try to be 100% correct, teach you what the right thing is, but the truth is, it's going to be a real small difference in most cases, because you're using an approximation. It's the thin-walled approximation. And we're lucky here that we don't have to change our units around, because we're just taking a pressure, which is 5 megapascals, and multiplying it by millimeters, 234 millimeters, and then dividing it by 8 millimeters. So
we wouldn't use 40 kilonewtons in this scenario?
Not yet.
Oh, no.
That's only for the bending. Or that's only for stress that's going to be caused by that force being moved onto the thing.
Okay.
It's this craziness right here. Right? The fact that they used capital P for the thing because they're a bunch of maniacs. The whole world is against us. We'll get over it though. Maybe. Or we won't. Something. So we have a substantial 73.13 megapascals. It's nothing to sneeze at. The longitudinal stress is just P di divided by 4t. So you really could just divide this one by 2, right? .56 megapascals. That's supposed to be an M. It's a special M. It's special. It's very special. Now I have to look at the other kinds of stress that we could possibly have. So at K, we're going to have transverse shear. And this is a hollow cylinder, so we can look this up, it's 2 over VA. See where that is in Chile. It's earlier. I should probably tag mine. I've only looked this up 1,000 times.
So what does the subscript T and L stand for the shear?
The T is for tangential,
Okay.
which is also known as hoop. I like the name hoop better. But we got the maximum shear here. Oh, by the way, the L is longitude. Use S for T and L. So we have tangential is the T, longitudinal is L. And this is right here is where we got for the shear diagram. So the area here is a little bit of a pain, but not too terribly bad. The force is going to be, let's call it 40,000, so 40E3. The area is going to be pi over 4, and we're going to take the outside of 0.250 squared minus the inside of 0.234 squared, right? And so I have 40, I don't need to do that one first, but I did it anyway. 0.025 squared point, did I say 0.0? I did not, you dummy, I think I did. 0.25 squared, 0.234 squared, subtract them, multiply them by pi, divide by 4, right? So we get an area, right? And then we divide, and we only get, it's not a lot, 6.577 megapascals. So I did all this in base units and then I divided by a million in my head, because that's what that M meant. That's the only, double checking, that's the only stress that's different. And then at L, we could have bending. It's going to be compression, so an MC over I. We could kind of do this in our heads, but we could do like a little mini FBD, where we're going to have shear coming this way, moment going that way, and it's going clockwise, so this bit would go counterclockwise. So here's your M, here's your R. So summation of moments, I'm trying to do the right thing, I'm trying to, it's kind of a little overkill. But we got the reaction moment is going to be that F times the height, which is going to be the 600 right here, right? So 0.6. So the moment is going to be, well, we could use the killa kills the milla. I like to do that sometimes. So we go 400 kilonewtons times 600 millimeters is an acceptable shortcut. And that's going to be 24,000, is that right? I don't trust myself. 24,000 Newton meters. Those are base units. So, and remember that this is going to cause compression, so I'm not going to bother with a negative in front of it, but 24,000. And now we need the radius of this, which is to the outside radius, so 0.125. And then we need pi over 64, and the 0.250 fourth. Tons of us make this mistake, including me, to be going too fast and using squared instead of fourth when getting a moment of inertia of something circular. I've done it a bunch of times and gotten angry at myself. But you got to be nice to yourself every now and then. Just be, hey, cut yourself some slack. This world's hard enough. I don't like this calculator as much as I like my other one. I think I'm going to run out of stack space. Times pi 64. think that's gonna be right. Let me see. So I think this turns out to be 3,000. Is that true? I'll do it the other way around. I like to do this. I divide it, and then I hit
Yep,
inverse.
3,000.
Was that?
Yep, 3,000.
So I think I get 67,000. Or 67, excuse me. 67 million, so 67.31 megapascals. And you might want to remind yourself that it's in tension.
Which positive?
No, I said compression. In my head, I was saying, I almost went Tennessee again. Or that was earlier today. That was in the dynamics class. I was just in this room, and all of a sudden, I just flipped over to Tennessee accent. It just kind of happened. Because I was visiting New York recently. I don't know, that doesn't make sense. That's okay.
How'd you get that outside radius again?
They had the outside diameter.
Oh.
I'm sorry, I did write it.
And why is C 0.125 in the bending?
Because that's the distance to the neutral axis right here. The radius of this, here's the neutral axis right here, and the diameter of this. This guy right here is only. This is a red herring. This right here just to mess you up. That has no practical use. That 200, that 150 millimeters. Not that I could think of. Anybody think of reason why?
Yeah, because it's not even an FBD. Would that even be useful?
No, there's no moment around there. It's a red herring, as they said. Now, is that a fish or is that a bird?
Red herring? That's a fish.
It's a fish herring, and not a heron. It'd be a red heron.
Yeah.
But why is it a red fish? Where did it ever come from? I don't know. That's not why we're here. Okay. But anyway, so
Could
now
we have
what
a fish exam? I'd prefer that.
was that?
Could we have a fish exam?
We could have a fish exam. I'm okay with that. I don't think it would really care about it much for here. Where's in this problem? Did they give us an X and a Y? If we want to be perfectly, yeah, they did. All right, so the X was in this direction. Let's see, are these one of these maniacs that goes Z in that direction? Z is in this direction. And then Y is in that direction. So if you're going to have a stress element, and we're going to have the one for K, all right, so this has got to be K, and he's going to be in the YZ plane, YYZ, maybe Rush fans, because I'm not.
I don't know that one. I'd love to see that.
You know YYZ? It's an instrumental. And it's the actually Morse code for YYZ, which is I think the Toronto airport. I can't even do it. Screw it up.
Rush is a great band. I wish I could have seen them live.
I'm surprised they haven't got it. There's 1,000 drummers that have been inspired by Neil Peart. So I'm surprised they won't find somebody that can play every single lick of it. Mm-hmm. Okay, so looking at that direction right there, it's because if you were to take a cut, or you're going to have a what I like to, the equivalent force and moment diagram that we would be placing onto this thing, you would see that you have a force right there is coming onto that thing. So here's where that stress element is. So you can see that's the direction. On the top face would be going in that direction. No, I think I just drew this wrong. Son of a gun. I was talking about YYZ and Rush, and I got the element wrong. Sorry. Not your fault, it's mine. There you go. Everything's my fault. So that's the X direction and the Y direction. So we would have, this is going to be the hoop right here, right? The one in this direction right here, which we found was 73.13 megapascals. And this would be the longitudinal, and there's nothing influencing this one right here. So he's 36.56 megapascals. And this guy is going to be the transverse shear, and he's just 6.577 megapascals. Whereas the stress element here is going to have the same 73.13 megapascals. But up above, you can see that this thing right here is so much larger than the longitudinal. So I'm going to write, now hopefully I'll make this one in the correct direction. This is going to be the L, right? And that's going to be the YYZ, if I get that right. Here's the Y. Here's the Z. It's a terrible Z. But we're going to have a compression right here. And maybe we'll call this sigma L Y is going to be our 36, that's a 36.56 minus, off the edge yet, 67.31. So, we get 36.56. So we get a negative 30.75. So this is the 30.75 megapascals. That's supposed to be a 30. So something of note here, this one would require us to do a little bit of work for its Morse circle. We're going to have something along these lines over here. It's going to be, I'll draw it first. I'll cheat a little bit here. Go over here. Because this one should be twice that one. And this is the larger one over here, but this one's going counterclockwise, but it's really close to being onto the edge right there. So you'd have something along those lines. Whoops, that's not a very good circle. Go back to like that. Stuff all over my finger. But this one would be really easy. So that's a good problem, right? Just to tell you. Find the Morse circle for that one. Because it'd be...
It's a 2D one.
Yeah, well, you can make it a 3D if you want.
Okay.
Right? Because this one is going to equal principal stress 1. And this one's going to equal principal stress 3. But we could still have principal stress 2 is equal to 0. So there's your 3D Morse circle. But you're only drawing that because you're demonstrating the fact that you recognize that the out of plane one is going to be 0. And also recognizing that because there's no shear, it's already the principal stress. That's a pretty good problem.
So this is what you meant by combining pressure question and
Yes. Yeah.
principles. So the full answer for this one, if you weren't including principal stresses, were the tangential, the longitudinal, the bending, and the transversal.
This I'd either ask that or I'd ask that. I wouldn't ask for both points, as it's just, you know,
Too much work.
yeah. I like to, generally speaking, I like to separate the principal stresses for, you know, a question, if I ask a principal stress question, because on exam 2 it comes up again. Because as I mentioned, in one of our failure theories is maximum shear stress theory, which you need to recognize the principal stresses. Okay. And you, so it comes back. And then also, sometimes I ask a pressure vessel question, but I don't have to. If I didn't hear, I would ask it on exam 2. Do you want to see a shaft problem? There are a ton in, not a ton, there's just enough. There's just enough in, let's see, We have one in here. All right, so this was too complicated. I'm always looking for the good combined stress problems that are just the right amount of complication. See, this one too is a bit too much, and it doesn't even have numbers. So these are all, it's under the list of computer problems. Here you go. Here's, I don't like the way they necessarily did this, but we're gonna try it again. We're gonna do it without their method. Okay, so you're not even seeing the thing I'm talking about. So there you go. I don't know what the hell that equation is down below it. Oh, maybe it has nothing to do with it. Okay, so here's problem 818 in Beer-Johnston. And so we have a 4 kilonewton force that's on one of the gears, or pulleys, or whatever the hell it is, some type of friction disc or something or other. Because if it's a gear, it should have forces in 2 different directions, because gear teeth, by their nature, have to, the total force has to be coming in at a bit of an angle because of the shape of the gear teeth. So it's always pointing down, pointing. Well, it always has a radial element to it, as well as a tangential one to the thing. So I'll draw it. And something that's also on my very high priority list as an instructor is trying to aid in identifying and helping to fix trouble with spatial visualization. It's a really, really important thing. And I think, I mean, this is just my opinion. I'm not sure if it's a correct opinion, but I think video games have made us worse at spatial visualization because the computer is doing the work of recognizing, transforming something from 3D into 2D, and vice versa. We don't get many opportunities to take something into 2D and transfer it into 3D. And it's a really important thing because when you're trying to figure out a complex system, you inevitably have a certain amount of things going in 3 dimensions that can get complicated, that you have to kind of visualize. I tell you, we need more Legos is what we need. So we have 4 kilograms. I love me some Legos.
I still buy some.
Yeah, I inherited myself, well, my sons. So we have, once again, they're using letters on here. I think it's obnoxious, but so. And what did we label this? A, B, C, D. A, B, C. A, B, C, and D. I'm not drawing the bearings, but you can see that the bearings are on there. Let's label the axes the way they have them. I think it's boring, but it's right. So they have X coming out that way, Z coming out this way, and our dimensions, I could look down here, 140, 80, 100. And then lastly, I think they gave us the radius instead of diameter. They have 60 and 90 to the center. Okay, so I think we're all set up. They want to find in the shaft, knowing that the inner diameter is half the outside diameter, duh, and that the allowable is 60 megapascals. Determine the smallest permissive outer diameter of the shaft. So we're not going to do that problem because this is a design problem. We will start getting into more design problems. It's an important, aspect of the thing. But first, we want to do analysis before we do design. So we're not going to do the exact same thing as them. But let's see if they have the answer in the back of the book, and let's work backwards to see if we can get near 60 in terms of our stress. So this is problem 818, and if we get lucky, or I could actually remote probably into my office computer because I think I have the solution manual to this somewhere. I thought they were right in here, and we were 818. They don't seem to have a pattern to them. They would be given all of them. No, they didn't do it. Look at that. You have 815 and 819. Oh, what number am I? Yeah, no, they didn't give it. You bastards. Let's see. I don't know if I'm going to put this. Let's see if I can get on remote real quick. Boom. It's going to let me in. No, it's not. I know it's wrong. I don't want to put this on the internet now. I've already breaking into my computer. Yeah, we're going to cancel. Yeah, anyway. Okay, so let's just pick a diameter of, we'll eyeball it at 20 millimeter shaft. So first thing, we have this unknown Q that we need. Let's shift to the. So in order to get that, we really would like to look down the shaft. So I guess looking from above makes more sense than anything else. So I guess I will look down and make that the X and that the Z. I'll include both gears to start with. They're not really gears. I don't know I forgot what they call them.
Pulleys.
So, are they pulleys? But they only have a thing on one side, right? Kind of weird. So that looks like it's in the X direction, in the negative X direction. So it's going to be, he's on the bigger one. So he is was it 4 kilonewtons or 40 kilonewtons?
4.
Sure, yeah, right. And then the Q looks to be in the negative Z direction, go out this way. So the sum of the moments about the y-axis is going to give us -4, and we can get away without turning this into millimeters at this point because we're really just going to come up with a kilonewton right there. So we have the radius to the big one as being 90. There to give us the radius, but okay. I was about to say we're going to turn the diameter. And then we're going to have Q times our 60. So we'll have Q. Four times 90 divided by 60. And it should be 6, which makes kind of sense, right? It should be 3 halves. Did that just move?
I accidentally.
Okay, cool. I thought it was an earthquake. So no, not that. And while we're here, it's good to get the torque that's on this thing. And to do that, you always have to expose the metal. So you gotta cut it to see the torque. Does that make sense? You gotta cut it to see the torque. So we will redraw this. But we'll only show the outside guy, and I'll even draw it like that right there to kind of say the shaft is now sliced in between so that we can expose the thing. So we still have this 4 kilonewtons, but in order for this to balance, that's gonna be a test. Okay. I need to get so that looks like it's going clockwise, so this must be going counterclockwise. We get the torque to be able to expose it. So once again, we'll say the sum of the moments about the y-axis is 0, but now we'll go negative, and this is kilonewtons, and these are millimeters, so we could still do this legitimately. And it's going to give us Newton meters. So the torque that we would get is, what's 4 times 9? Is that 30? Is this 360?
Yes. Negative 360.
So 360 Newton meters. So we get the torque. That's good news.
Wouldn't that be kilonewton meters?
Well, see, these are millimeters.
Oh.
So the kilo kills the milli. That's how I like to say it because it sounds funny, kind of.
So would that cancel out? Or
Oh,
that,
up here,
they cancel.
the millimeters cancel each other out, so that get this. That gets it. A lot of times, like I don't know, a couple years ago, I wouldn't have done that. All right. I'm going to keep this orientation here, even though it's kind of obnoxious, the things being straight up and down. I don't know. I like to have the shear diagram. I'm going to turn it over. I'm going to flip it over. I just made this. We're going to rotate it over because I like to have the shear moment diagram right here. So it's a little bit of a tester with our dimensional sense. I'm going to go with the X, Y. This drives me nuts. That's what X is right there. But did I get? Does that seem? Let's see. I'll draw this thing out. Let's see. So I'll draw it this way and I'll erase it. So we have the small one's going to be to the left, and the big one's going to be to the right. Whatever we're listening to. I'm going to play some music during this. But then, if I were to put it on YouTube, it would be not taken down. We wouldn't be able to make money off it. I'm not going to make money off it anyway. And then while I have this up here, might as well see. Can I draw it? Maybe they'll be able to see it. Look at the YZ. Yeah, so I think the YZ. If we look at it this way right here, Z, Y. Do the same thing. Look a little bigger. And the dimensions, we'll put them in here. 100, oh, this has been here. 80 and 140. And then label the forces. Now this is a really important one. Be careful here. And the X, Y, I think we're going to be seeing this coming down that way. It's going to be our 4 kilonewtons. And then this guy is going to be 6 kilonewtons. So we need our reaction forces, and that's going to be racks. And this is going to be rids. Rigs. I can't pronounce that. RDX. Mr. Unpronounceable. Here we're going to have an RA Raz. And this guy's going to be a rids. Not all the time can you figure out what direction these are going to go when there's multiple forces on here. This was not too bad. I guess I'll do it down here so I don't have to erase stuff. But I'll take the sum of the moments about A first. And that's A in the, technically it's the AZ. And so we're going to start to go first a -4. And we're going to end up with we'll keep it in millimeters here, so we end up, our answer will be in kilonewtons. And so there's 4 kilonewtons times 180. And then we're going to have plus R dx times 220. Is that right? Anybody want to add 180 to 140 for me? Maybe that's 320. Bueller? Yeah, that's right. Anybody agree? 180 plus 140, or we get 240 plus 80. Yes, okay, cool. So we just take 4 times 180 and divide by 320 and get 2.25. kilonewtons. And then the sum of the forces in the x direction is going to be RAX and then minus 4 and then plus 2.25 equals 0. So our RAX is equal to 1.75. Should be able to do it in my head. In a similar way, some of the moments about A, but now this time about the X direction. Is there any questions as I'm going through, like, why did you do that? How'd you know to do that?
Why is it for the first one, the moment of AZ, why do we use RAX and RDX? Oh, right, because it's going to.
Yeah, we want to eliminate this reaction right here. So we're taking the moment about A,
Gotcha.
and we're doing it in about the Z axis.
Gotcha.
Gotcha. Okay, cool. And this one we'll always go counterclockwise as positive. So we do the same thing, but now it's going to be that's going to be counterclockwise, right? So it's going to be positive 6. I don't need to put the extra sig figs in there, but times 100, and then minus R dz times at 320. RdZ is going to be 600 divided by 320, or that's not much, 1.875 kilonewtons. And then the sum of the forces in the Z direction, writing at a weird angle. We'll say R AZ minus 6 plus 1.875. So that R AZ is 4.125 kilonewtons. Save my purple. Use my light green, that's no good for most things. Wow, that was terrible. That's going to be good enough. All right, so running out of colors. We're having a blue. Blue, where'd you go, man? Oh, I probably left him behind. Never leave a man behind. I'm so sad. I like the light blue better. Just a little change of pace. We'll go with brown. Shear moment diagrams. And I guess we're going to switch back to blue. We have this guy going up, and this RAX, he's kind of small. He's smaller than that guy, he's a little bit bigger, right? So this is going to be, RAX is 1.75. We'll go V, and we'll write what these are, kilonewtons, so we can remember. These are V. I'll write kilonewtons here too. And this amount should be 2.25, or a negative 2.25. Over here, this RAZ, he's much bigger. And he is in the positive Z, so he's 4.125 kilonewtons. He comes up, and then this is relatively smaller compared to him. And so this is technically negative 1.875. So this one's going to have a smaller slope than that one. And our mission is to find what these points are right there. So that's going to be, once again, these are millimeters and these are kilonewtons. So we're going to be, if we multiply them to get the area that's inside this right here, that little spot right there, we will end up with Newton meters, which is what we really want. So 100 times 1.75, I think, is 175. Is that a stupid thing to ask out loud? Hey, look, it is 175 Newton meters right there. And we don't have to go from this direction, but we could, just to prove it to ourselves. And we could take our 1.75 and multiply it by 180, and we should get this value right here. So let's just try it, 180 times 1.75. And we say that this should be 315. But if we took the 2.25 and multiplied it by the 140, we should get the same thing, and we do. Right? Because this area right here, or no, I'm just saying this area right there should equal that area right there, to get it balanced out, because this is simply supported, so the moment must carry out. This one down here is going to be fairly steep, where it's not going to be as steep right there, and I'm doing a terrible job of that. But we want to get both of, we'll take the 4.125, multiply it by 100, I'm feeling bold, 412.5. These are Newton meters as well. And it's easier to go to the other side, so it's 140 times the 1.875. And that should be 262.5. And now we want to get the maximum moments. I think I can, people at home are getting shortchanged, that's all right. You didn't come here, what the hell? So we have the moment that is taking place at B, because I forgot, this one is B, and this one is C right there, right? And that's B, and that's C. The moment at B, the combined moment is going to be 175 squared plus 412. So I'm thinking this is going to be the bigger one. And so we have 175 squared and 412 squared. Add them, take square root, and we get 448.1. Getting tired. 448.1. These are Newton meters. But just to be on the safe side, let's look at the other guy here. He's 315 squared and 262.5 squared.
Or 412.5 should be squared in the first one, correct?
Yes, thank you. And this actually gets pretty close, but not quite. 410.0 Newton meters. So this is the max one. We really only care about the maximum because we want to find out where the thing's going to break. So, so we got the stress, bending stress, MC over I.
Those signs should be flipped on the diagram, right?
What are you saying? Where?
Like the 1.87.
On the shear one?
Yeah, because this is negative. This is positive Z.
Oh, okay.
It's good. Keeping track of it. Absolutely. So we have 448.1, and we decided arbitrarily to make a 20 millimeter shaft. We'll see if our arbitrary works. We want pi over 64.02 fourthed. And so we have 448.1 times 0.01. Now we're going to have to do a little bit of work, 0.02. I'm going to take it, raise it to the fourth, multiply it by pi, divide it by 64, and divide that whole thing by there. Oh, you get a large stress. Don't know if it's right or not. Maybe. So I don't think our 20 millimeter shaft is going to survive. 570.5 megapascals. Wee, big. Our torsional shear, TR over J. The torque that we got was 360. So 0.01 for the radius. And pi over 32. Should have kept that other number, right? We could have saved ourselves a nanosecond. Maybe a little bit more. No, we'll read that up there.
I can move the camera.
It don't matter. Well, we could pan, right? Go like. I'm getting motion sickness. Now it's in your way again, isn't it? You just moved because it was in your way. Now I put it back in your way. I'm a bastard.
Well, I was hitting it before, so I didn't want to hit it.
I got you. Okay, you didn't want to give me like some motion sickness there. So I got 0.02 for raise it to the fourth here. Losing my train of thought. Pi times that. 32 divided? Sure. And then divide it again. Yeah, big number. 229.2, call it, megapascals. Now for a stress element that you would label with this, it's hard to say what plane that stress element is going to be in. Because we're actually taking and kind of rotating the two planes. We had this plane, and it's somewhere in between those two planes. We do know that it's aligned with the y direction though, so we could put a y right there, but we can't commit to anything. And because of this moving a plane, we decided to kind of ignore transverse shear. Just because it turns out it's not going to be a whole lot, and it's like a longer thing than is necessary to do to work. It's just not worth it. And this is actually going to be, this bending would actually be tension and compression. Tension on one side of the shaft, compression on the other. If we had a pool noodle with us, we would be able to see how that's bending out of those two planes. And then we could start picking it. Now, the torsion, we should point out the torsion is only between these two pulleys. It only exists between here. So I'm not sure where I usually say this in the semester, but it's sort of like, we want to deep dive and try to really look at the thing. This is an approximation because these pulleys actually have a width to them. So we're making it kind of fast, so we're kind of ignoring their widths. and we're saying there's going to be a stress element, and we know that it's going to be at B, so there's a stress element somewhere really close in there where it's going to both have the torsion and it's going to have that bending stress in there. So truth be told, it doesn't really matter which direction that we decide to put this in. We could try to piece it together and think our way through it, but it's going to be something like that. And so you would say that this is going to be 570.5 megapascals, and that this would be 229.2 megapascals. So a really complete problem, but not an exam problem. And by the way, this is too long for an exam problem.
Okay, I was gonna ask that.
I mean, it's just not practical. So sometimes I'll just go 2D. Sometimes I'll give you one of the sets of reaction forces. Makes things a little easier. Sometimes I've divided it into separate problems, but I've kind of committed being only 3 problems.
So for making the stress moment diagrams, to find out which direction like Q and the 4 kilonewtons, which way they go is clockwise is negative, counterclockwise is positive.
Yes, that's correct. Yep.
That's how you figure that out.
Yeah, yeah. So for these guys over here. What you're talking about?
Yes.
Yes, yeah.
And say for like on the YZ plane, we were to put the Z in the opposite direction. Could we reverse like the direction of that? Like the reverse direction.
Well, okay, so what you would be doing is you'd be flipping the whole thing over 180 degrees. Is that what you're talking about?
Yes.
That we decided to look at it from, let me see, which way did I decide to look at it? I'm looking
basically
at
on the back side.
this way right here,
Yeah.
but if I came around and turned my head around somehow, which way that way right there, everything would be the same. It would just be flipped.
Okay, and you'd be okay with us doing either way, as long as we don't mess up the sign.
Yeah, I just want, and it's not the major highlight of the problem, but I would like going like, okay, hey, there's a difference between like what you can do on a test and what you could actually do if you given time, right? Because you're under pressure during an exam. So I'm not taking big points off for necessarily that, but I would like to that might be something like, hey, maybe you want to work on spatial visualization if you're getting that wrong, right? And to work on more problems along those lines.
And tau is just that tau is not transverse.
No, it's only torsional shear.
That's torsional.
Just torsional. And like I said, the transverse is going to be relatively small compared to the torque, the torsional shear. Most things will break in torsion I don't think you have many situations. It's really, well, I would say transverse is second cousin to direct shear. And so sometimes if something is the supports are very close to each other, then transverse becomes like something that could be significant compared to the other stresses. Because when the supports get closer to each other, bending doesn't become as important because there's less of a moment that's happening. So there's some rule of thumb about like when you can ignore a transverse, which is like when the ratio of the diameter to the length is like 1/10 or something like that right there. But I haven't seen that repeated very often. So most people just write the problem and say ignore transverse shear. We might see again soon why. So we got like a half hour left, is that right?
It is 8:30.
Yeah. Very tight. What kind of problem would you like to see? Door handle? They don't have as many door handles as I would like to see. But in this section right in here, there's a problem. I have asked this as a homework problem, I think. Yeah, okay, so here we go with problem.
I have to head out.
Okay, no problem, thanks for coming. You're welcome. Here is a problem, let's see, he is actually 39, right? So he goes, this is a pipe, it's not under pressure. If you wanted to make it a crazy combined stress problem, that would make, once again, it'd be way too long. And even, no, I think, I don't think I could say that I've never asked for a problem this hard, but it's actually, well, there's got a couple extra forces on there. I just noticed I forgot to say that there's some extra forces on there that we might want to take a look at. Those 150 and 50-pound forces that are coming from the Z direction. This, again, one of the important beginning steps is that spatial visualization, to be able to draw 3 views of this thing and then be able to get the reaction moments is definitely an important skill set, and not every statics instructor or mechanics and materials instructor is asking for these things. All right, so we're looking at stress element there, stress element there. I don't know what these things are supposed to be. Oh, that's supposed to be like an elbow, okay. And our axis is X coming down the length, which I like, and Z coming over this way. Y coming that way. And, oh, I'm sorry, did you move the camera?
No, I just moved the camera.
Thank you, appreciate it. All right, so let's see. We got a force that's right there, and a force that's for some reason right here. And this is the 150. And this is the 50. Then we have a force coming in X direction of 150. And this direction, the Z direction, I think it looks right. 200, is that 200? Yep. And then get some dimmies on there. 4 inches, 6 inches. Four inches, 6 inches, and then 10 inches to get up there. And did they tell us that it's equal? Okay, so we got the inside diameter. Nice that they made. Is 1.61. Outside diameter 1.91?
Yeah.
Not 1.90. And anything else? Determine the normal and shearing stresses at H and K. Well, H is right here outside. No, H is on top. H and K. Great. Whew, that's hard to read. I can just move the camera around. All right, so I would first start off with 3 free body diagrams. I like X and Y first. And look at this and see what forces we could see. The only force I think I can see is going to be the 150. What do you think? Did I miss any of them? Not going to be able to see that 150, not going to see that 50, not going to see that 200. So I think I'm good.
That's just the reaction forces.
Yeah, we just put the reactions on. And so I'm going to call this guy my Rx. And then this is easy enough because I can pick out my moments. This guy is going clockwise. So this guy's going to go counterclockwise. And I'll call him MZ. And I could do my sum of the moments about the z-axis equals 0 and take mz minus 150. Whoops, I didn't do my dimensions on this, so let me see. Right there. So that's going to be, well, it's actually interesting because that's going to be, we could get, it's 10 in that direction, 10 in that direction. But we had, this was 10, and then this is 10. But this is the 10 that matters, right there, right? I wouldn't put this, I'd put it different because I'm going to test to see if you knew which moment arm that you were going to get for this one. So I think I can do the MZ in my head, maybe 1,500. I always do the dimension first instead of the force. It's just a habit. But I think the standards usually go force and then dimension. Because I first got introduced to a torque with a torque wrench, and those were labeled as foot-pounds. So I was like, think of them as, that's how I don't know, is the thing. But I do Newton meters in SI. I don't know. It's a quarter newtons. Just a quarter. Meter newtons. Nobody ever does meter newtons. That's just insane. No one would ever do that. That's just crazy. So let's see. So in the XZ plane, it gets a little boring. The only thing exciting about it is, for some reason, we have 200 coming down that way, and we have a 50 coming this way.
So they would cut into each other, and you basically get a sum of 150.
Yeah, and
Going
what's even
clockwise.
going to be a little weirder is that we have a 150 coming over here.
And that's different because it's at a different distance away from the moments.
Yeah, so you just got to be like a little careful here to think your way through all of these right here. So it's going to have like no reaction in the Z direction force, but it might have a moment. So it's a little bit of a trick, right? So, I mean, you could test yourself with the thing with the sum of the forces in the Z direction equals to 0. And when in doubt, if you're not sure, this guy is going to be your savior, right? And double checking the thing, because you don't want to be caught out cold, right? So you go negative 150, but then negative 50, and then positive 200, and then we should draw, let's just draw in the positive direction. If you don't know something, pick the positive direction. And the same thing's true with our moment, and the moment, positive moment, is going to be in that direction, so we'll actually go an MY right there too. We're going to need in a second, but I forgot to put it in here, so I'm going to go positive RZ equals 0. And then you write RZ is equal to 0, right? You just see that they cancel each other out. Same thing with the sum of the moments. Take it about the y-axis. And we say my. And we'll have a positive 150 times, we didn't dimension this off, but it's going to be 4 inches here. And it's going to be 6 inches here. So that's going to be times the 4 inches. And if you want to be 100% accurate, you would go minus 200 times 10, and then you go plus 50 times 10. But we just know that that's going to be. So let's double check and see does what M at Y turns out to be, whether it's positive or negative, right? So we have, I'll go 150 times 10. So 1,500. And that's going to be negative, right? But that's going to go over to, so we're going to take 150 times 4, all right? And so that's going to end up with a MY of 900 inch pounds. Pound inches. if you're a normal person. And then the last one.
Those moments are like the actual moments. They're not like the reaction.
No, those are the reaction moments.
Those are the reaction moments.
Those are the reaction moments. And if we're going to be correct right here, we're going to say we chose this to be counterclockwise, and it was counterclockwise. Whoops, I'm sorry, right there. And we chose this one to be counterclockwise, and it was counterclockwise. Let's take a look at this last one here. And that's going to be in the YZ plane, right? And let's see what's going to be on it here. Well, we would see this guy right here at 200 pounds. 150 is coming at us from what we're looking at here, that 150. But we're going to see two of them right here. We could combine them together if you want, where we could just say that this is going to be 200 pounds right there, right? So, being careful with our reactions here. First off, let's just choose a reaction that's in the positive direction here. This is the RZ, which we already showed was going to be 0 right here, right? I'm just drawing it on there because we don't have anything, we don't have a reaction in the Y direction because we don't have a force in the Y direction. We did have this RX that we never bothered with, but was 150 pounds.
So does that mean there's not going to be a moment on the X?
No.
No.
Because we're going to have this reaction moment right there.
Right.
So this guy wants to go counterclockwise. So this one's actually going to go clockwise. So here's MX. Remember, that's special because it's aligned with the long axis. So that's also going to be the torque when we get done with it. So we could go sum of the moments about the x-axis, counterclockwise is positive. We're going to say we have 200 times, we didn't write the dimension, but I believe that's 10, yep. 10 inches right in there. And then the reaction moment we wrote as clockwise. So the reaction moment is 2,000 inch-pounds. That looks like a period, inch-pounds. And that's going to be clockwise. Now, when we go, and if we ask for a equivalent moment diagram right there, let's try to set it up as best I can. I'm not doing a great job right there. Right, so here is where we have cut this thing off right here. And here are axes. Maybe I'm going to move the axes over to that right in there. So the torsion one, this was clockwise. So on here, it goes counterclockwise. And if you ever need to know, thumb points towards that way, right? And so this is going to be the 2,000 inch-pounds. And the same thing is going to be true over here for our moment about the Z. It would be counterclockwise, but it's actually counterclockwise, right? So because this was counterclockwise, so this one has to be clockwise, so it has to come back over to that way right there. And that's 1,500. And of course, we had this one. That's counterclockwise, but it's actually, because it's counterclockwise here, it's got to be clockwise here. My fingers are wrapping around that way right there. 900 inch-pounds. And then in terms of forces, it's simply going to be 150 pounds in that way. And we can see that all the other forces canceled out because there's nothing going to be in the RZ direction. Nothing going to be in the Y direction. There never was anything. So that right there is your equivalent moment diagram.
And that's what you want as a final answer.
And sometimes I ask for it. I don't always. I'm always trying to keep it the exam. I can't ask everything I want to ask. It's just not, it's gonna make the exam too long. So, but the real thing that we want, maybe we want a stress element out of this. We want to pick one of the stress elements, and we start going down the list. First off, notice, what about transverse shear?
There is,
There's none,
yeah.
right? Because we really need to be in the Y direction or the Z direction to get anything out of it. And then, all right, so axial stress?
Yep.
Sure. So we're going to get F, that would be the Fx over A. And this is obnoxious, right? So I'm going to put them up here. So we get what? 1.90 squared minus 1.61 squared. While we're doing it, go pi over 64. Oh, thank you. Very sure that.
Gonna be reviewing this later.
Was that?
I'm gonna be watching.
Okay, good. So 1.9 raised to the 4, 1.61. Whoops, enter 4. I think I just screwed that up. I gotta do it again. Damn you. Yeah, I did screw it up. 1.61 times pi. I did that again right there. Look at that. Do that all the time. Somebody should please calculate this. See if I got it right.
I got you.
Thank you. This is fourth. Oh, I did. I remember. I did do that. I did mess that up. Oh. I'm very, very tired. It's why I like Excel. I just fucking put the thing in once. Do it once. 1.9 squared.
0.799.
0.799?
995. It's a weird one.
Yeah. And I could probably make that one work. No, I'm not gonna. I keep screwing this up, man. I should not. I don't know if I should drive home. I'm so tired.
Got an Uber.
Yeah, the Uber would be like, dude, Westbrook, I want a tip. I said, I do this every day, man. Stop.
0.3099. Right?
Yeah.
Okay.
All right. So we're just going to take 150. That's not going to be very big, is it? Yeah, it's really small. The axial. 150. Oops, come on, buddy. Don't do that. 0.79995. Boom. So just 187.6 psi, and that's in tension, but not a lot. The bending. Now we have to decide which one we want to look at. None of them are. I mean, it's not that big. I guess we look at the worst one, which is going to be this, the moment to the Z. So that's going to be at H. That's going to be the worst spot, right? So at H, we go MC over I. And so the moment that we would use for H. And this is an important step right here, right? Making sure that you have the right moment that causes the stress. It's a point of interest. So you get 190 divided by 2 and divided by 0.3099. I still don't think it's going to be a very large stress. So
Is H it's the top square, correct?
the top square, yeah.
Yes.
So we do get like we get 4,598. And here's an important thing to do. Is it gonna be in tension or compression?
Tension,
It's gonna be in tension.
because it's on the outside.
Easiest to see, well,
Or,
yeah, it's because this would, you could think of this as pulling down on it. Yeah, yeah. You could also, without ever doing this, you could also see from over here, you could think of the stress element being like right there, and you can see that is pulling down on it as well, that moment. I think, for whatever reason, this one is easier to visualize than that one. So this technically is an unnecessary step on one level, is just seeing if you can visualize what's happening to the thing. In terms of technically speaking, you don't need to do this. Except that if I would ask you to do it.
I assume later on we're gonna be moving those H and K to like other points.
We're gonna just pick the worst spot. We're not gonna pick a particular stress element. We're gonna say, we're gonna combine that and that together, just like we do with the shaft, right? Because we wanna get the worst, we wanna find out where it fails. So that's where it's gonna be the stress, where it's at the maximum stress. But we're not gonna do the transverse again, because that's a pain in the ass. So we're just keeping it as a stress element here on this thing, just so that we can kind of like go, can you visualize how these stresses interact with each other? And then the last one here, we get the torsion, just to see what we get, TR over J. We know that J is very fortunately equal to 2 times I, so 0.30992 times, so 0.6198 inches fourthed. So the torsion is 2,000. The radius still 1.90 over 2, and we have 0.6198. And so I think I get, did I only get 3? That just seems small. Seems way too small.
That's 200, not 2,000?
That should be 2,000.
That should be.
Yes, it'd be 3,000, about 3,000.
3,060.
Yeah, I accidentally plugged in 200. It must have been what it was. I couldn't read my own handwriting. And be careful not to put tension or compression here. It's not. It's not. It's only normal stress is tension and compression.
It's just.
Yeah, it's just which way is it?
Torque.
Which way? Yeah, it's just a shear on the thing. So you would combine these two together because they're both in the x direction. So do it below whatever sigma x. Very small, but 4,598 plus 187.6 for 598, 187.6 plus, so 4,786 psi. But might as well go KSI on this. And so as a stress element that we're looking at, it's H, and we're looking down in the XZ. I think I got that. I got it wrong before, so I'm not 100% sure I got it right. So we could write that this is 4.79 KSI. And whatever you do, do not put a stress in that direction. Warning. That's a 5-point mistake. Just so you know, out of 25 or whatever, 30 or something. It's a
what if we say 0
it's a
and
big,
we don't give it an arrow?
That's fine. But it's, you don't know, you're missing out on like what's actually taking place. Right? But you know, once again, it's not a punishment. It's an assessment of your mastery of the material. So it's not, you know, I'm not trying to be punitive ever. It's mostly like I need to evaluate, like, you don't get that, right? Like, yeah, you use the wrong You use the wrong moment right here. Use the wrong moment here. Use the wrong force here. It's telling me you don't quite see what's going on. But you get something a little wrong here. It's difficult sometimes to see the difference between a procedural error, just a little mix-up, and a confusion about what's going on into the thing. It's just the nature of it. Okay, and I do like to see the correct arrow on this one. Like I didn't care on the shaft so much, but on here I like to get this. I'm more concerned about the visualization on here. So you can see that torsion is going across that face right there, causing it to be onto that face.
Okay, yeah.
And that's a lot easier to see on this than it is necessarily on that one. That's amongst some of my play for saying this right here. But this in the long run, this isn't like a critical thing to be like have mastery of to get that arrow the right way. But for my priorities at this point, it's sort of like the visualization of this, demonstrating that you can navigate and see where the stresses are, and see which ones are opposed with which ones. I think is even though it's not something that people will like be asking you to do all the time, it would still be something that's going to be akin to that visualization that you would need. Okay. I don't know if I have to try to feel as though I want to try to explain every fucking thing.
Rated R.
Yeah.
So as long as we understand the problems we just went over, we should be fine for the exam.
I think so. But here's a problem with the word you just said. Not understand. Do. Yeah. Okay. So I mean, I know what you mean. But so many students come to me after they failed an exam and go, but I understood all of the solutions, right? And there's this huge difference between seeing a problem for the first time and getting through it, as opposed to looking at it and saying, "Oh, I see what you did there. Oh, I see what you did there." I mean, they might as well be miles apart.
Yeah.
Because until you've actually done it and pushed yourself to do it. So that's why I go so much. I don't even like when people say, "I'm going to study."
Practice.
I'm going to practice. I'm going to challenge myself to see when I get a problem, brand new problem put in front of me, can I get through it? Because that's what I'm testing. Is can you navigate through a problem? Not if I were to make it multiple choice and you may be able to understand which answer to pick out of the things. Maybe I don't know. So along those lines. But
so the homework that we just handed in, that has less priority than what we just went over for everything.
Yes, absolutely. Because we didn't do any curved beams and we didn't do any contact stress.
So
and because I don't usually want to ask a ton of questions. And I don't, okay. I mean, maybe someday, if someone's listening to this, if I post it, that maybe I will go back on my word to those people in the future. But for you right now, I have no intention of trying to see how long I can make this exam. Okay. And testing what I consider important things to know about, but not necessarily critical things that I want to measure right now.
Would those be on the second exam?
They might be on the final exam.
Okay.
But it wouldn't be something. I mean, honestly, it's just to see like, hey, are you well-rounded enough to pick up something that's deep in your memory banks and gonna go, oh yeah, I know something about contact stress. Honestly, some of the reason why I bring up contact stress is because we bring it up in ME370. And then you'll also see we're going to have some other topics where we do some deflection things. I want you to have experienced it, but I don't necessarily want to test it because I have other priorities.
Okay. I got you.
All right, guys. I know you'll do great. I will try to grade the stuff that's still ungraded. Is that the stuff that I just turned in? Have I graded 3 homework grades?
I think
Yeah.
so. Yeah. I think you graded it late last week. Maybe Thursday.
I don't know. I just want to grade.
Yeah.
Okay. All right. So I'll try to look at 4.
I got a quick picture.